In this video, we're going to talk about normal distributions, which are sometimes called the bell curve, and in particular, the 68, 95, 99.7 rule, which is sometimes called the empirical rule. All right, so a normal distribution, like we've talked about before, is symmetric. It's the same on both sides, or at least pretty close to the same on both sides, and unimodal, which means it has one peak right there in the middle. This is sometimes called a bell curve because it makes a bell shape. Many things follow a normal distribution. Many things, when you graph the data, look like that. For example, people's heights. Like most people are going to be just kind of average right here. So that's the most people. But a few are a little taller, and a couple are like really tall. And same thing on the short end as well. Or, for example, the amount of Skittles in a bag. Not every bag of Skittles has the exact same amount. Like, they probably all have generally the same amount, but there are a couple that are a little higher and a couple a little lower, and that's a normal distribution. Or usually, like class test scores. Most people are right there in the middle with a few high, a few low. That's what people mean when they say they're grading on a curve, because it's a bell curve. All right, or like body temperature. And I wanted to show you this. I saw this the other day. They did an experiment at Stanford University and found that our body temperature is actually usually not around 96.8. Our body temperature is usually more around 97 point something. I forget exactly what it was, but it's a little lower than we usually think it is. So body temperature follows a normal distribution. It makes a very tall, but it's still a bell curve. Most of our body temperatures lie somewhere within this zone, but a few of us have really high temperatures, and a few even have a fever, and then a few have kind of low body temperatures. All right, so real quick, since it's symmetric, if you draw a line right down the middle, that is going to be both the mean, the median, and the mode. It's the mode because it's the most. It's the median because it would be the middle number, and it's the mean because if we averaged all this up, it would also fall right in the middle. So the mean, median, mode are going to be the same, and then 50% of the data will be below it. 50% of the data would be above that mean or median. So there's symmetry, mean, median, mode are the same, and 50% of values is less than the mean, 50% above the mean. So keep that in mind. And then we can actually break the data up using standard deviations. So remember, standard deviation is a measure of how spread out is the data. And it gives us a good way to kind of count out from the mean. So let's say I have a normal distribution, and let's say that the mean is right here. By the way, come in. Just give me a second. So the mean, we've been using x bar, but there's actually another symbol for mean, and it's this. It's called mu. It's just another Greek letter that we sometimes use for mean. It looks kind of like a U with like a line right here as well. So this is the mean as well as this. Typically when you see this stuff written out, they use this symbol rather than this one. So I'm going to use that mu symbol. All right, so this is the mean. Let's say I add a standard deviation. I'm going to put mean so you know what that is. Let's say I add a standard deviation to the mean. So I add one standard deviation, or let's say I go back a standard deviation. So take away a standard deviation. How much of the data do you think falls like from here to here, from -1 standard deviation to +1 standard deviation? So it turns out that is always, from here to here, that is always 68% of the data. It doesn't matter what it is. If you're talking about Skittles or heights or temperatures, if you find the mean and then you go up a standard deviation or down a standard deviation, it's always 68% of the entire data. So like if we're talking about heights, this would be 68% of people fall within a standard deviation of the mean. If you go out another standard deviation, so like +2 or -2, that is almost everybody. That is actually 95% of the entire population. And if you go out one more, so +3 standard deviations or -3 standard deviations, that is actually really, really close to everybody. It's 99.7% of the data, always. That's why that standard deviation that we found in the last unit is important. It can tell us this stuff about the data. So note that there are a few lingering out here, like there's an additional like 0.3% on either end, but that's almost everybody. 99.7% of the data would fall from -3 to +3 standard deviations. So that's called the 68, 95, 99.7 rule. You do need to memorize those numbers, by the way. Okay, so here's a slightly better looking picture than what I had drawn. So here's an example. Imagine the speeds of cars on a highway are normally distributed. Normally distributed is important. That tells me it's going to be a bell curve. If it didn't tell me that, I wouldn't be able to do any of this. But that tells me it's a bell curve. The mean is 70 miles per hour, so that's what goes in the middle, right here. And the standard deviation is 10. So if I take 70 and I go up one standard deviation, basically just add 10, now I'm at 80. Or if I go down a standard deviation, I would be at 60. So between 60 and 80, that is 68% of the cars. 68% of all cars on this highway are going somewhere between 60 and 80 miles per hour. If I go up another standard deviation, I'd be at 90 or down to 50. That's 2 standard deviations away. And again, 95% of the data is within that range. So 50 to 90 miles per hour is 95% of the cars. And then if you do one more, so up to 100 or down to 40 miles per hour, probably not anybody going outside of that range. That is 99.7% of the cars. So we're going to use this to answer these questions here. What's the probability that a car picked at random is traveling between 60 and 80 miles per hour? That would just be this, 60 to 80, which was the 68%. What's the percentage of cars that were traveling between 70 and 90? Okay, 70 and 90 is actually right here. And just because they're one away from each other doesn't mean we automatically use the 68% rule. Like, these rules don't move. They have to stay where they are. The only thing I know that has to do with the 90 is that I know from 50 to 90 is 95%. Like, I know from here to here is 95% of the data, but I want just 70 to 90. The good news is this is symmetric. It's the same on both sides. So I could just cut it in half. And I know that it's going to be the same on both sides. So if the entire thing from here to here is 95, then if I just want this half, just cut it in half. So do 95, but cut it in half, and that would be 47.5%. Which basically is just this sliver right here. Is 47.5, and this is 47.5, and together they make up the 95. What's the probability that a car picked at random is traveling more than 100 miles per hour? More than 100 means just this tiny little sliver right here. All I know about the 100 is that from 40 to 100 is 99.7% of the data. So, obviously all of the data would be 100%. So if I do 100% minus the 99.7%, that leaves me with just 0.3% that is outside of this interval right here. However, that also includes this little piece. But again, since it's symmetric, I know it's the same on both sides. Just cut it in half, and you'll get just this sliver here. So take the 0.3% and cut it in half, and you get 0.15%, and that's what this little sliver is here. This is 0.15%, this would be 0.15%. If you add it to the 99.7%, that would be 100%. Just one more example here. The scores on the ACT are normally distributed with a mean of 21, so that's what goes in the middle. And I really recommend drawing out your bell curve, so it's easy to visualize. So mean of 21. This time the standard deviation is 4, so I'm only going to add or subtract 4 each time. If I add 4, I'd be at 25, and then at 29, and then at 33. If I subtract 4, I'd be at 17, and then at 13, and then at 9. So once again, from 17 to 25, that is going to be 68% of your data. From 13 to 29 is 95% of your data, and then from 9 to 33 is 99.7% of the data. So what percentage of students scored between 13 and 29? 13 to 29 is exactly that 95%. Come in. Just have to see if I'm almost done. Number 2 is your score needs to be better than at least 84% of students who took the test. You scored 26, will you get in? A 26 would be right here. And I don't know anything about 26, but I could figure out something that has to do with 25. So let's maybe go with that. So how do I figure out like all this probability working up to 25? Well, first, don't forget that you could always just split the data in half. I know that, let's use a different color. I know that this lower half of data is already 50% because it's just half the data. So all I need to figure out what I'm getting to 25 is I need to figure out this little sliver right here. How much is just this piece? Again, the only thing I know that has to do with 25 is that from 17 to 25 is 68% of the data. So I know like from here to here is 68%. So if I want just this sliver, I'm gonna have to cut that in half, and 68 cut in half would be 34%. So like this little sliver right here is 34%. All right, so if we add up the 50 plus that 34%, we are currently at 84%, which is exactly what I was needing to be better than. So if I made a 26, which is slightly higher than that 25, then I'm in good shape because I did higher than 84% of everybody. All right, one final problem. What's the probability that a student selected scored between a 17 and a 25? That one's an easy one. 17 to 25 is just the